Good morning. Warping a PS seismic image to align reflectors with a PP seismic image can cause wavelet distortion. Usually, to reduce this wavelet distortion, a shaping filter is applied after warping. We propose a new method to reduce this wavelet distortion that applies a filter before and after warping, but this method also allows us to estimate the PP and the PS wavelets. First, I would like to call your attention to two continuous signals, P of t and Q of t. Now, if we were to convolve these signals with the wavelet displayed by the impulse response shown, we would get F of t and G of t. Now, if we were to squeeze G of t to F of t, we would get wavelet distortion. So how can we reduce this wavelet distortion? Well, let's look at P of t and Q of t again. If we squeeze Q of t to P of t, we would see no wavelet distortion. Now here, when we squeeze, we multiply the squeezed version of Q of t by a factor of 2. And this is simply because when we squeeze the delta function as shown above, we have to multiply by the factor we squeezed by to get back to the original delta function. Now, before we squeeze in this case, we apply an anti-aliasing filter, because as you all know, an impulse will have a frequency spectrum out to Nyquist. So if we squeeze in the time domain, we're going to stretch this frequency spectrum past Nyquist and gain to get aliasing. But with anti-aliasing filter, we prevent this. So with this idea of squeezing impulses with no wavelet distortion, we can construct our warping with wavelets algorithm. But before I get into that, I want to define some variables. The vector f is our reference trace and is simply f of t sampled at uniform increments of time. The same rule applies for the vector g, or our trace to be warped, and the vector h, our wavelet. Now, one term I haven't defined yet is a of t, which is our inverse wavelet to our wavelet h of t. Now, the next topic I would like to cover is convolution, which I know you all know pretty well. So let's say we were to convolve A with G, and let's say A has 3 elements and G has 5 elements. Well, we could write this convolution in matrix form as simply matrix A times the vector G, where the matrix A contains time-delayed versions of the vector A. Now, because, as you know, convolution is commutative, so we can also write this as the matrix G times the vector A, where the matrix G contains time-delayed versions of the vector G. Now, as I said before, convolution is commutative, so A times G equals G times A. Now, I bring up this property of convolution being commutative because I'm going to be referring to it quite frequently in the rest of the presentation. So, what is warping with wavelets? Well, let's start with the simple case of squeezing G to F. Warping with wavelets would require us to convolve the vector G with the inverse wavelet A. Our next step would be to squeeze this deconvolved trace to F. Now, this squeezing operator will be represented by the matrix S, which is linear and time varying. Also, the anti-aliasing filter that I've referred to before is included in this matrix S. And when we apply this matrix S, we yield the following result. Our final step in warping with wavelets is to convolve with the wavelet H to yield no wavelet distortion. Now, because the matrix S is a time-varying operator, S and A do not commute, meaning that HSAG does not equal HASG. In fact, since A and H are inverses of one another, the matrix H times the matrix A is simply the identity matrix, reducing this to the following form, which is simply warping. So in this case, we knew what the wavelets were. But how can we estimate these wavelets? Well, in fact, the warping with wavelets algorithm gives us the means to estimate these wavelets. And to remind you again, warping with wavelets is simply convolving the inverse wavelet with G, then squeezing this deconvolved trace and convolving with the wavelet H. So to estimate our wavelets, in this case, we only need to estimate one wavelet because A and H are inverses of one another, and as you all know, if we estimate one wavelet, we can easily solve for its inverse. So in this case, we're going to solve for the wavelet A, or the inverse wavelet A, by multiplying the matrix A on both sides of the equation. Now, because A times H is the identity matrix, as I said before, this reduces to the following form. Now, because convolution is commutative, I'm going to switch around AF and AG to get the following form. And then I'm going to move SGA over to the other side and factor out the A. So we're left with this quantity, F minus SG. So what is this quantity? Well, we refer it to as the difference matrix D. So what is this difference matrix? Well, if A has 3 elements, then the difference matrix D would have three columns. And these 3 columns would be D0, D1, and D2, where D0 is simply F minus S times G, and D1 is F delayed by 1 sample minus S times G, also delayed by 1 sample. And the same rule applies for D2. So to give you an idea of what these vectors look like, I'm going to calculate them for our simple case of F and G. And the result would be these following vectors. Now these vectors are different. And to show you these differences, I'm going to zoom in on each one of them. Here's D0, which has a different waveform from D1, which has a different waveform from D2. Now it's these differences that allow us to estimate for our inverse wavelet A. If we were simply shifting G to F, then D0, D1, and D2 would be time-delayed versions of one another, which would not allow us to estimate for our wavelet. So you may have noticed before that the matrix D times the vector A equaling the 0 vector has the trivial solution of A equaling 0. Well, we chose to get around this trivial solution by setting A0 equal to 1. Now I could have set A0 equal to anything. Let's say I set it equal to 100. Then the wavelet H that we would estimate would simply be scaled by 100, meaning that we cannot estimate the true amplitudes of our wavelets. We can only estimate their shapes. So we can reduce the following equation to the following form. Now in this case, we have as many equations as samples in our trace with only, in this simple case, 2 unknowns. So we choose to solve this least squares problem by setting up the corresponding normal equations. Now the matrix that I've highlighted in red is not a Toeplitz matrix. And this is simply because D1 and D2 are not time-delayed versions of one another because we applied the time-varying S operator to time-delayed versions of G. This matrix, however, is symmetric positive definite, meaning that we can solve for the inverse wavelet A by using Cholesky decomposition. And once we have an estimate of our inverse wavelet A, we can estimate our wavelet H. The known wavelet is represented by the solid line, and the estimated wavelet is represented by the dots. Now, I said before that we cannot estimate the true amplitudes of these wavelets. That's why the amplitudes in this case have been normalized. But as you can see, the shapes of these wavelets are the same. So how do we apply this process to PP and PS images? Well, first, we are going to need a couple of PP and PS images, which were provided courtesy of Sinopec. Now, before we estimate the PP and the PS wavelets, we normalize both images because we're not quite sure what type of amplitude gain has been applied to these images during processing. Now, before I get into estimating wavelets, I want to redefine some variables. The vector f is no longer a trace, but is an entire PP image, where the vector g is also the PS image. Now, the vector h is the PP wavelet, and the vector a is the inverse PS wavelet. Now, in this case, there's no reason to believe that the PP and the PS wavelets are the same, meaning that h and a are no longer inverses of one another. So what does this mean? Well, as we did before, we estimated our wavelets by starting with the warping with wavelets algorithm. And to remind you again, in this case, it's going to be convolving the PS image with the inverse PS wavelet, squeezing this deconvolved image to the PP image, and then convolving with the PP wavelet. Now, I also want to point out that the squeezing function used in this case was constructed by using estimated time shifts from smooth dynamic warping, which was proposed by Dave Hale and Stephen Compton. So before, we were able to multiply the matrix A on both sides of this equation to eliminate one of our unknowns. But we can't do that here because A and H are no longer inverses of one another. So what we choose to do is use an iterative process to estimate our two wavelets, which was probably our simplest attempt at solving for these two wavelets. But before I get into the iterative process, I want to show you how we can solve for one wavelet if we knew the other wavelet. So in this case, let's assume that we know the inverse wavelet A. So our next step to estimate H would be to compute what we call Q, which is simply SAG. Now, because convolution is commutative, we can switch H and Q as shown, and then construct the corresponding normal equations to solve for our wavelet H, because we have as many equations as samples in our PP image. Now, the matrix Q transpose times Q is a Toeplitz matrix, meaning that we can use a fast Toeplitz solver to solve for H. So let's look at the other scenario. What if we knew the wavelet H? How could we solve for A? Well, because convolution is commutative, we can switch A and G, as shown, and construct what we call the matrix P, which is simply HSG. Now, what is this matrix P? Well, to know what P is, I want to remind you what the matrix G represents. The matrix G simply contains time-delayed versions of the PS image, which would mean that the matrix P is similar to our difference matrix D, where we're applying the squeezing operator multiple times to time-delayed versions of the PS image. Now that we know how to construct P, we can solve for A by setting up the corresponding normal equations. Now, the matrix P transpose times P is not Toeplitz, but it is symmetric positive definite, meaning that we can again use Cholesky decomposition to solve for the inverse wavelet A. So now we know how to solve for one wavelet, knowing the other wavelet. So how do we start this iterative process? Well, we start it by setting the inverse PS wavelet equal to an impulse, which is equivalent to setting the matrix A equal to the identity matrix. Now, this is essentially what you would do if you were simply trying to find a shaping filter to shape the squeezed PS image to the PP image. So now at this point we can compute Q and then solve for H. Now this completes one iteration of our algorithm, and the resulting wavelets would be the following. Now, I want to remind you that the PP wavelet is simply a shaping filter that shapes the squeezed PS image to the PP image. Now if we apply this shaping filter to the PS image, we would get the following result. So what do we do for the second iteration? Well, first we compute the matrix P, and then we solve for a new estimate of our inverse wavelet A. And then once we have this new estimate of A, we can solve for another estimate of H by computing Q and then solving the corresponding normal equations. So let's say we fast forward this process to 11 iterations. Then we would get the following PP and PS wavelets, which are significantly different from our wavelets from our first iteration. So next I want to show you what the warping with wavelets algorithm looks like if we use these PP and PS wavelets. So first we start with the PS image. Our next step is to convolve this PS image with the inverse PS wavelet. Now you probably don't see much in this image because there's an abundance of high frequencies. So I'm going to split up the squeezing operator S into its anti-aliasing and squeezing parts. Here's the anti-aliasing part, and here's the squeezing part. And then our final step with warping with wavelets is to convolve this image with the PP wavelet. So what this algorithm is trying to do is solve for an A and H that minimizes the differences between the squeezed PS image and the PP image. And to give you an idea of how it's doing, here's the PP image for reference. I'll just flip back and forth. Here's the squeezed or the warped image, and here's the PP image. So next I want to compare, or I want to walk through the three different types of warping methods that I've showed here today. Here is simply warping. Now I want you to notice that the image SG is significantly noisier than our next warping method, which is applying the shaping filter. Now this is simply because the shaping filter is shaping the squeezed or the noisy squeezed PS image to the less noisy PP image. Now next I want you to focus on how this image, constructed by the shaping filter, is very close to warping with wavelets using wavelets with 11 iterations. So because we're trying to minimize the difference, the RMS difference between the PP image and the squeezed PS image, or I mean this warped image, I want to show you how the RMS differences change with the number of iterations, starting with the shaping filter, where one iteration represents the shaping filter and 11 iterations obviously represents the image I showed you. Now we see that there is some change, that we're getting closer to the PP image. But where are these changes occurring? So this caused us to split up the image that I showed you into its shallow and deep part as we defined them. Here's the deep part overlaid on the PP image, and then here's the shaping filter. Now I want you to notice how there's not a lot of difference between this image and our 11 iteration image. Now if we go back to our relative RMS difference plot, we see that there is basically no change in the deep part in the RMS differences. So let's look at the shallow part. Here's the shallow part overlaid on the PP image. Here's the shaping filter. Now I want you to focus for these small differences that you will see. Now you may have not seen them then. I didn't even see them in this monitor right here. So let's zoom in on that part. Here's the PP image for reference. Here's the shaping filter. And then here's 11 iterations. Now to give you another look at that, here's the shaping filter. And here's 11 iterations. So what causes these differences to occur? Well, to answer this question, we looked at the amount of squeezing that's applied to the PS image. Actually, hold on, before I get to that. Here's the RMS change of the shallow part, which is where we see a significant change in the RMS. So where do these RMS differences occur, or this change in RMS differences? Why do they occur? So to answer this question, we looked at the derivative, or simply the amount of squeezing that's applied to the PS image. Now you'll notice a high amount of squeezing applied in the shallow portion of the image. And if we take the shallow rectangle that we defined to define our shallow part and overlay it on this image, we see that it highlights that area with a high amount of squeezing. So we suspect that the shaping filter cannot account for the two different types of wavelet distortions created by the two different amounts of squeezing, while the warping with wavelets algorithm can. So today I've shown you how we can apply warping with wavelets to PP and PS images. But this algorithm is not limited to this. It can be applied to any geophysical transformation that involves squeezing and stretching. An example of this would be NMO, which we have done tests with. Also, two differences of the warping with wavelets algorithm from other methods are that we apply this squeezing operator multiple times to time-delayed versions of our trace or image to be warped. We are also convolving the inverse PS or the inverse wavelet before we squeeze in this case. Now these two differences reduce wavelet distortion, but they also allow us to estimate our PP and PS wavelets. Thank you. I'll take any questions.